Hello, student. Uh, so, okay. So, actually, in our physical interaction session, we have seen we have seen how to apply. Actually, we have memorized. Okay, we have memorized how to apply Kirchhoff voltage law to a circuit circuit to analyze. Okay. So actually, this can be say that it is a nodal analysis. Okay, this is a nodal analysis technique. Okay, so actually we have get a simple uh, example. Okay, so I can't remember the exact example we have taken. Okay, but anyhow we will take this kind of one. We have like this. Okay. And here, let's say that this resistor is 4 ohm, okay, and this voltage is 6 volt, the battery voltage, okay, EMF, electromotive force of this battery is 6 volt, and it has 1 ohm internal resistance. And let's say that this is 2 or something, 2 ohm, this resistor. Let's say that this is 2 volt, okay, and there is no internal resistance for this battery. Okay, so if we use the Kirchhoff voltage law to the circuits, okay, we can uh, we can represent the current like this. Okay, and we can apply the Kirchhoff law here. So you know that so so when you consider battery, this minus to plus, you can consider minus to plus direction. You can consider as plus direction. Okay, you can consider as plus. Okay, and the current is going from plus to minus. You can consider it as a minus EMF. Okay, so if we see in this way, in this direction, so this battery, it is minus to plus, so it will be plus EMF, so it is 6. And if you consider this one, it is plus to minus. Okay, this is minus to plus, so we have considered it as a plus EMF. Okay, and so with respect to this one, this is my plus to minus direction, this direction. Okay, so it will be a minus EMF. Okay, so it will be minus 2. Okay, and it is equal to the resistance drop of the resistance drop, voltage drop between the resistance. Okay, so we have I, okay, 2 plus 4 plus 1. Okay, so basically we can get I is equal to 4 by 7. Okay, so this is a simple example to illustrate how to apply Kirchhoff voltage law to a circuit to analyze the current and voltages. Okay, then I ask you to find the voltage between these two terminals. Okay, between these two terminals. Okay, so how to find it? Okay, so before going to that part, okay, uh, I will remind you one thing. Okay, so if you consider a battery, okay, if you consider a battery with the internal resistance, okay, so internal resistance is, we can represent this internal resistance in series with the battery. Okay, so if you consider a battery with EMF, and the internal resistance is simple R. Okay, so that battery can represent like this. Okay, so these are the two terminals of the battery. Okay, these are the two terminals of the battery, not this one and this one. Okay, these are not the terminals. This will be the terminals of this battery. Okay, because that battery has an internal resistance. Okay, so this internal resistance also with this battery, inside this battery. Okay, so this is the terminals of the battery. Okay, so this will be the plus terminal and this will be the minus terminal. Okay, okay, so say that if you connect this battery to a load. Okay, if you have connected this battery to a load. Okay, so what is the practical scenario? Okay, what can you say about the voltage between this battery? Okay, so if you connect it to a load, maybe a bulb or something. Okay, when the current is flowing through it, due to this internal resistance, the voltage will be dropped. Okay, voltage will be dropped. Okay, so it will be uh, less than the E. Okay, the voltage will be, this two terminal will be less than the E when uh, the battery give a current to a load. Okay, so that is the practical scenario. I think you have already known this. Okay, for example, if you consider a 12-volt battery with 1 ohm resistance or something. Okay, if you connected this 12-ohm battery to a load. Okay, so the voltage between these two terminals will be dropped. Okay, it is less than 12 volt. Okay, so how to find that? Okay, how to find that? Actually, we have a little confusion when we are developing the when we were developing the equation. Okay, we have a little confusion there. Okay, but actually that is the our logic is correct. Okay, our logic is correct at that time. The only thing is the direction we have uh, take wrong. Okay, but the expected value will come. Okay, should come at that time also. Okay, so I will explain it. Okay, so let's say that, so if you have connected this battery to a through a load. Okay, that means a current will be going through that load. Okay, so a current should be emit from this battery. Okay, the current should be emit or drawn from this battery. Okay, so current is flowing out of the battery in this way. Okay, let's say that current is I. Okay, so you know that it is a battery, no? Okay, so again, after going it in different node. Okay, different load, finally again the current should come here, and that current also will be same, no? Same. Okay, to the battery. Okay, okay, so if we try to develop an equation for this. Okay, let's say that this terminal is A and this terminal is B. Okay, so the voltage, not the voltage difference. Okay, the potential is, let's say that it is VA here, and let's say that it is VB here. And let's take this point. Okay, so this is not the battery terminal. This A and B will be the battery terminals. Okay, so this is a logical point actually. Okay, let's say that that is V. Let's say that that is C. Okay, and the potential is VC. Okay, so so you know that if you consider a battery. Okay, in the same notation you can use. Okay, you can use. Okay, you can say that uh, minus to plus, it is plus value. Okay, so here the potential is high. Okay, so VA minus VC will be E. Okay, the voltage between these two terminals, this is logical terminal actually. So it will be VA minus VC. Okay, and it is equal to E. Okay, so if you consider this one, so you can see that the current is now the current is flowing from B to C. Okay, so the voltage should be high here. Okay, and the voltage should be low here, because in this way there should be a voltage drop. Okay, so if I put Ohm's law, V equal IR to this branch, or to these 2 points, between these 2 points, B and C, it will be VB, because voltage is high. VB minus VC will be IR, I simple R. Okay, so to find, okay, actually we mistake this direction. Okay, at the interaction session. Okay, so you can see that if you want to find the voltage between the battery terminal, that will be VA minus VB. AB, AB, the voltage between A and B. Okay, to find that one, so let's say this is 1 and this is 2. We have to subtract 2 from 1. Okay, so we have to subtract 2 from 1. Okay, then we will have this VC cancel out. We will have VA minus VB is equal to E minus IR. Okay, so you can see that V, okay, in this case, the voltage between this, the battery voltage, the terminal voltage will be V. This is between the terminal, two terminal of the battery, will be equal to E minus IR. Okay, so you can see that the voltage is less than the EMF value. Okay, the uh, less than the EMF, electromotive force of the battery. Okay, so this should be remembered. Or I think this this is a common sense, no? You can remember it. Okay. Okay. So if you want to find the voltage between these two terminals, also you can find the same logic. Okay, so you can write the battery like this with the EMF and the resistance one. Okay, and you have another resistance here. Let's say that this is R and R. Okay, so here the I is flowing like this. Okay, so let's say that this is VA, this is VC, and this is VB or something. Okay, so in the same manner you can write that VA minus VC is equal to EMF E of the battery. Then VB minus VC, because the current is flowing in this direction, VB minus VC is equal to I R plus R. Okay, so if you want to find the voltage, you can reduce this uh, 1 from 2, so you will have VA minus VB. Okay, so that is the voltage between these two terminals is equal to E minus I R plus R. Okay, in this way you can find that. Okay, and you can see that the internal resistance is also in series. Okay, so both this you can take as internal resistance, and you can write this using this one. Okay, no need to go through like this. Okay. Okay, okay, okay. So let's say that if you want to find the, okay, and another case. Okay, so let's say that what happened. Okay, so you have a circuit like this. Okay, so you have a electromagnetic force, and this is the internal resistance of the battery. Okay, and these are the two terminals of the battery. Okay, okay, so let's say that now the current is going inside the battery. Here the current is coming out of the battery. So the current, the load is drawing, okay, the 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 voltage is drawing the current from a battery. But here, the current is going inside the battery. Okay, at that time, what happened? So you can say that in common sense, this voltage should be greater than the E. That is why the battery EMF power is not is strong. There is another battery, there may be another battery, and that effect is is strong. So at this time, a current is flowing through, current is flowing to this battery, okay, into this battery, not out of the battery, okay. So at that time, how to finalize this one, okay, how to find this one, okay, the same theory you can find, you can take, okay. So here you have the voltage VA. Let's say that here you have voltage VC and here you have the voltage VB. Now you have to find the voltage difference between VA and VB. Okay. So if you consider only the battery, okay. Again, if you consider battery, only battery, okay. If you consider the only battery, okay, this E should be from here to here, okay. So VA should be high. Okay, so if you can say that VA minus VC is equal to E. Okay, so that is this point and this point. Okay, so this is a logical point. Okay, and you can see that now the current is flowing to from here to here. So the voltage difference should be in this direction. Okay, so VC should be high. Okay, so then VC minus VB is equal to the current. Let's say that current is I, so it will be IR. Okay, so to find VA minus VB, you have to add them. So this VC cancel out, then you can get VA minus VB is equal to E plus IR. Okay, so the voltage now between the battery terminal will be E plus IR. Okay, so this is the situation when the current is flowing into the battery. Okay, so the voltage is greater than the EMF of the battery. Okay, okay. Now, if I ask you to find the uh, voltage between this B and C, what is the value? Okay, B and C, what is the value? Okay, so you can see that you can apply the same property. Okay, same theory. Okay, so here the current, if the current is flowing here, the now at this point the current is going inside the battery. Okay, but this battery doesn't have a internal resistance. Okay, so if you consider this one or this one, actually we have to consider this one, no? In this case we have to consider this one because the current is uh, going into the battery. Okay, but the R is 0, no resistance. Okay, if the R is 0, always the battery voltage, okay, battery terminal voltage is equal to the EMF of the battery. Okay, if the internal resistance is 0, any cases. Okay, if the internal resistance is 0. Okay, so so you can see that if the internal resistance is not there, when the battery is given a current, there is no voltage drop. Okay, so this voltage drop happen, this voltage drop happen due to the internal resistance. Okay, so practically every battery has a internal resistance. Okay, so if you connected the battery between two terminals, the voltage will be dropped. Okay, so that is the practical scenario. Okay, so I think that is okay for you. So if you consider this one, the voltage between the B and C will be 12 volt again. Okay, because there is no internal resistance. Okay, so as a homework, uh, try to find this one. Okay, I will change the direction of the battery like this. Okay, the same one. Okay, Here, let's say that it is E1. This is capital R. The internal resistance is R1. Okay. And the same manner like this. This is E2. Okay. E2 internal resistance is 0. And here you have another capacitors. Let's say that R1. This is R2. Okay. So find the voltage between A and B and C and D. Okay, so try to do this as a homework. Very easy. You can do that to remind the things you have learned. Okay. Okay. So that is so here you have to use the Kirchhoff voltage law. Okay, and there is a Kirchhoff current law also. Okay, actually that is called mesh analysis. No, that is related this mesh analysis. Okay, I can't remember this correctly. Please refer your note. Okay, then you can get it. Okay. So anyway, the Kirchhoff law, the Kirchhoff current law said that, okay, if we have a point in a circuit, okay, so if we have different current come and going from this through this point, the algebraic sum will be zero. Okay, that means the current come to the point. Okay, current come to the point. The sum of the current come to the point is equal to the outgoing current of the point. Okay, if this I1, I2, I3 come, okay, and I1, I2, 4, 5, 6. Let's say that 4, 5, 6. Then I4, I5. Let's say that this is in direction I5, I6. Okay, so algebraic sum will be 0. Okay, so I think you can remember these things. Okay, so if you get a very simple example, okay, so if we have this kind of resistive load, okay, okay, resistive load, let's say that in this way, okay. So here you have, let's say that you have 24 ampere, okay. Let's say that here it goes around 16 ampere, and here it will come. So here you can see that you can apply the KCL here, right of current law here. The current coming to the point should be equal to algebraic sum of the outgoing current. Okay, so 24 current is coming here and 16 current is going here. Okay, so the coming current is 24. Okay, and outgoing currents are 16 plus another current, I2. Okay, so I2 is 8. Okay, so here you will get 8 current. Okay, so if you take this as the input current, okay, then 24 plus I is equal to 16, then I is equal to minus 8. Okay, so that means it is again coming to going out of the point. Okay, so you can consider it any direction in any way. Okay, but you can get the same answer. Okay, so so this will be, if this is 16, so this will be 8 ampere. Okay, so let's say that this R and this are uh, same. Okay, so 8 is coming here, and what about this current? Because this R and R same. Okay, so here you can see that this point and this point also is same. Okay, there is no resistance between. Okay, so the voltage between these two resistance will be equal. Okay, so the same current will flow through two resistance. No? So this current will here go 4, and here also you will have 4 current, 4 ampere. Okay, so 4 ampere is coming to here, and 4 ampere is coming to here, and 16 ampere is coming to here. Okay, so what about the current from here. Okay, so 4 ampere coming here, it is coming into the point, and 16 coming here, that is also coming toward the point. Okay, so 4 plus 16, 20 ampere coming toward the point. Okay, and the coming current should be equal to the outgoing current. Okay, here only you have only one outgoing path. Okay, so here you have 16 and here you have 4. Okay, so both current will be going through this branch, that is 20. Okay, and here also you will have 20. Okay, and it is come to here, and if you consider this one, you can see that this is coming into 4, coming current 4 currents is here, and 20 ampere is here. The both currents are coming towards the point. Okay, and it should be equal to the outgoing algebraic sum of the currents. Okay, so only one branch is available to to go in those current. Okay, so whole total current, this 4 plus 20 will go through this branch, so that will be 24. Okay, likewise you can apply just current law to find the current of the each branch. Okay, and sometimes you have to use if you have complex circuit, you have to use the both uh, theories laws to analyze the circuit. Okay, so I think uh, in your note you have many examples, so you can go through this and you can remind your past learning things. Okay, so actually I want to do this lecture because I have done a mistake when we are deriving this expression. Okay, for the battery terminals. Okay, voltage between the battery terminals. Okay, so that is why I put this video. Okay, so you can refer them and you can clear your doubts. Okay, and so actually in this course we are not focusing to analyze the DC circuits. Okay, we are focusing to analyze AC circuits. Okay, and I think some theories are there again. The nodal and mesh analysis, nodal analysis, Thevenin's equivalent circuit, superposition theorem. Okay, so there are many theorems and techniques to analyze these circuits. Okay, so please try to remember these things. Okay, in your the uploaded lecture. Okay, it is uploaded by Dr. Udesh. Okay, so that is very the good lecture, completed lecture, complete lecture. Okay, please go through it. Okay, uh, please go through it and try to uh, remind the things you have learned. Okay, and we will start the AC analysis part. Okay, so we have to deal with the LRC component. Okay, with R means in resistance. Okay, and L inductance and C capacitance. Okay, so already you have learned these things. Okay, but so this can be connected seriously and parallelly, and the combination of series and parallel circuits, parallel connection. Okay, so you have to analyze these circuits. Okay, so there are different techniques to analyze these circuits also. Okay, so next week we will start from that. Okay, from that. Okay, thank you.